The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, hope you had all a good weekend. It was very lovely. We had a lot of fun during the weekend. Recall what we were talking in the last lecture. We discussed the Maxwell equations. Electric field, this is a very magnetic field, generate electric field. Current generate magnetic field. And what Maxwell added is the displacement field that the time derivative also generate magnetic field, right? So this set of four equations from the Maxwell equation, and one comment that I thought I forgot to make is this is actually called macroscopic Maxwell equation, and you can write atomic Maxwell equation that does not involve the displacement, because displacement, recall, is the polarization due to external field plus external field together, right? It's the response of the atoms to the external field. And similarly, magnetic induction also include magnetic moment and magnetic field. So the atomic Maxwell equation, actually you can go to write without those D and B, but you have to sum up over all atoms, and you do not use the concept of dielectric constant. And this is in fact the area that we're currently trying to work on. To build a bridge between the heat conduction and electromagnetic wave, because we're doing experiment when two surfaces are really, really close, like 1 nanometer close. Originally, we're using the macroscopic Maxwell equation, but in this regime, we're no longer we're questioning whether that's valid or not. So, but coming back, from this set of macroscopic Maxwell equations, we can find a plane wave solution for the wave propagating in a homogeneous media. A homogeneous media means I have the permeability and permittivity independent of space. So it's a function of frequency, but it's independent of space. And in this case, the wave vector, when we substitute back into the equation, we find the wave vector is related to frequency. That's a dispersion relation through the permittivity and permeability, which when we normalize to vacuum values, we have the relative dielectric constant and relative magnetic permeability. And so this is the square. So if I take the magnitude of the wave vector, right, this is a vector. Magnitude of wave vector, I can write this equation in terms of omega, and omega equals ck. That's what you're familiar with for free space, right? The wavelength times frequency equals speed of light. That's what it gives. And this n is the refractive index, the optical constant of the material. And different material have different optical constant, but it's not a constant. Okay, n is very frequency dependent, so it's a misnomer. So if you take the derivative of n, normally we take only the positive root. So most of the cases, don't worry about it. It's a positive root. Refractive index equals square root dielectric constant and relative magnetic permeability. But say in optical frequency range, this is 1 usually. So it's really just the square root of dielectric constant. And because this one could be including imaginary part, so when you take a root, generally your optical constant have a real part and an imaginary part. And the imaginary part is associated, particularly epsilon r, the imaginary part associated with the loss. And correspondingly, this kappa, which we call extinction coefficient, is also associated with the loss, the damping of the wave when it propagates through the medium. And we said that if you check, basically these are all characteristics you can derive from the equation, right? This plane wave solution, and if you plug in plane wave solution, you find that this is E. You can also use that find the H. Then E is perpendicular to H. So that's the two fields are perpendicular to each other, and it's perpendicular to the direction of propagation. And that's why electromagnetic wave is a transverse wave. It's perpendicular to the direction of propagation. And also, normally, it's a right-handed wave because it's E cross H gives you the K direction. And that's when you take the square root as a positive. And negative square root is just a recent invention. The theory was there, but let's say it was really, this matter-material field is based on designing artificial structures so that when both epsilon and mu are negative, you should take a negative square root. We commented at the end of last lecture. So this is where we were. It's basically giving you the vector equations. And if you recall, before this, we're looking at the electron. It's a scalar wave. We're looking at the electron reflection at the potential step, right? So we give you reflectance and transmittance at the interface. And where we're going is doing the same thing. I have electromagnetic wave comes towards the interface. What's the corresponding reflectance? What's corresponding transmittance? And similarly, after that, we go to acoustical wave, right? And acoustic wave is a more complicated EM wave because it has three polarization: longitudinal, which is the same as the K vector, vibration direction, and two transverse. So that is even more complicated. And but we're going to at least give you some idea of those all different waves actually behave from wave perspective actually very similarly in terms of the behavior. So let's continue. And what we want first is further looking at the wave propagation in homogeneous medium. And if you use the Maxwell equation, this is what you can prove. And I'm not going to write the math because it's very involving. You write vector. Let me just point out. So when you use Maxwell equation, what you can do, you can multiply h to this equation. What you see, B is mu h, right? So that's 1/2 mu h squared. That's like the magnetic field energy, stored energy. And if you multiply this by E, and what you have here is the epsilon, D is epsilon E, right? So you get a 1/2 epsilon E squared. That's the electric field energy stored. And when you add them together, the left-hand side will give you the rate of change of energy stored in the system, if you take any system you apply it. And the right hand should be the flux that going through across the system boundaries, right? So that's an interpretation if you do your math operation. And what you find out is then that flux of energy going across the system boundary gives you the energy flux of electromagnetic wave. And this is the pointing vector. Pointing vector is E cross H. So E cross H is the energy propagation direction. Okay? And if you think about my electric field is varying as a function of omega t. So instantaneously, my S, the energy flux, right, pointing vector gives me the energy flux. I should not say the energy. Really should be power flux. And what I have here is is a function of 2 omega, time-wise, right? Because if you look at the E is I omega, and if you have 2 sine omega times each other, omega t times each other, you get 2 omega t. So the energy, the power flux here is a rapid changing function with time, because the frequency of light, visible light at least, you know, is 10 to the 14 hertz. So 2 omega will give you even much faster, right? So in this case, normally we don't care. We can't measure. We cannot measure the instantaneous power here. And what we measure is time average power. So if you go to do your time average, and no proof, but it's much easier if you calculate this way. It's equivalent, okay? Is E cross H complex conjugate. And if you go to think about the mass flux from the Schrodinger equation, we wrote it as also real part of say Poisson and the gradient of a Poisson complex conjugate, right? So you see the similarity between those different flux. I'm writing this as a E cross H complex conjugate. Okay, so all those say this is a time average pointing vector, and now let's look at if I have the plane wave propagating inside the medium, right? How it will change, how the pointing vector change as a function of space. So let's say I have a plane wave, and I'm careful taking my coordinate. This is z direction. That's the direction of propagation, and this is the e direction is in the x. So x, y. So y, then say I would expect my magnetic field will be pointing E cross H, gives me Z pointing out. Okay? But you can prove it, right? You can use your E, let's say my electric field in the EX omega t as so it's an X component, right? Electric field pointing to X direction only. And the magnitude of the electric field times exponential mass I. And if you replace K relation here, what do we have? K equals omega C0n. So I can take out the omega. So omega t minus n C0 times Z. This is writing my plane wave for electric field in the polarized in the x direction, propagating in the z direction. Okay? So from here, if I know Ex, I can go back here because I don't know H, right? I said that H is a function is only in the y direction only. And in fact, you can use the Maxwell equation to prove it. So to find the H, I use the first equation, right? The curve of electric field. So I can say here, what I have is a unit vector x, y, z, and have d dx, d dy, and d dz, right? So this is the for calculate the curve, and I have Ex, so x component only, Ex 0, 0. That's the left-hand side, right, of the first equation. And the Ex is a function of z. Remember, Ex is just the vector direction. It's not a function of x. It's a function of z. If you look at here. On the right-hand side, I have b is mu, so say mu dh dt. So I have dhx dt, and this is the x direction, dhy dt y direction, dhz dt z direction. Right? So I'm writing out the first equation there. Vector. Okay. And now if you look at it, I said this is a function of z time and z only. So I don't say it's only a function of z and time. So if I take a derivative of this, of course, the x component. So x, I take out this, I have all 0. Right? So that means hx is 0. Right? Hx is 0. And then I look at the, if I look at the z component here, so d0 dx, that's 0. Dex dy, but the ex is a function of z only. Right? So that's also 0. So I have hz 0. So this validate what we're talking. It's a transverse wave, and h is perpendicular to e. I only have the second term, the y term, dhy dt, because the y, if I look at this, right, a vector, so I take this 2 out. So I have this 0, d0 dx, and then I have dex dz. This one is not 0. Right? So I have really minus mu dhy dt equals minus, this is the second term on the first row, so my sign is minus. And then I have, this is a positive, this is another negative, is minus dex dz. Right? So I know my ex. I have given my ex, dex dz. I take the derivative. I integrate it with respect to time. I get my hy. Right? So let me write down hy. In this case, what you get, without going through the intermediate steps, my hy component is E0 times n mu C0 and exponential minus I omega t minus n C0 times z. So again, it's a wave propagating in the z direction, right? And there's only y direction component is not 0, so it's perpendicular to the electric field. And in fact, if you look at E0 times this, essentially is my Ex, right? E0 times those exponential factor. This is my Ex, not the vector, it's just the form in the x direction. So in fact, let me use this right at the n mu 0 C0 times Ex. But say this is the magnitude of Ex is not the vector Ex because the component is in the y direction. Okay? So that's Hy, right? When I do my Poynting vector, I will need all 3 components. So that's why I'm writing it out. And in fact, what if you have a positive sign? If rather than negative, that's a forward propagating. If you have a backward propagating, and your corresponding sign here in the front will also change, and you'll have, in that case, you'll have hy equals negative and mu c0, mu 0 c0, and exy. And this is for negative propagating wave, a sign change. And that's understandable because what I have here, right, this is a propagation direction. I said it's a right-hand wave. So E cross H is pointing out. But now if the wave goes the other direction, H will point in the opposite direction to form my right-hand wave. Okay. And I commented when both E and I say mu and epsilon are negative, right? You have to do your left hand. And if you look at this, here Hy, if mu is negative, right, that changes direction, a real direction of the magnetic field. And similarly, if epsilon is negative, that changes real direction. So the negative root is actually of this refractive index here is actually the requirement from the Maxwell equation itself. There's no, it's just a math requirement, right? So it was the first pointed out by this Russian scientist Verstnakov, if both epsilon and mu are negative, you should take the negative root. But the later materials all have, say, epsilon mu pretty close to vacuum. So epsilon mu r is 1. So normally people say that's just an academic exercise until in the 90s, people start to actually make artificial structure have a magnetic resonance so the magnetic response resists the external magnetic field, and that could generate a negative mu. And in this case, when you can design material with both epsilon and mu negative together and become negative. Okay, so I'm not done yet. I have my Ex, I have my Hy, and I can go calculate pointing vector, right? So let's calculate the pointing vector. And so this is the complexity with vector waves. You have to do always vector operation, right? If you look at your pointing vector, okay, and at the end you'll find out this is the only z component. There's no x, y component because your Ex is in the x direction and the H is in the y direction, and the cross product is only in the z direction, right? So let me skip that vector form and just say this is a time average vector in the z direction. Is 1/2 real part of E now Ex Hy complex conjugate. And this is what you get if you write all these three components and you only have the z direction component. So now I can plug in Ex and Hy, right? And you have to be careful. This n refractive index or optical constant has both real and imaginary part. So when I take a complex conjugate, this one I take complex, this one I take complex, this I take inverse, and this n I have to take complex conjugate, right? So you have to do all that, and you say I omega t minus I omega t because plus I omega t. So I omega t cancel, right? E is negative I omega t, right? Because that slasher, because I was doing time average, time should not be there. So this always cancel time. And so what I have then is 1/2 real part of E0. That's the electric field, and exponential negative is positive n, and C0 times Z, that's the first EX. HY is E0 complex conjugate, N complex conjugate, divided by mu 0 C0, and I take a mu is pretty much as in vacuum, and then I have an exponential, and this becomes a plus I, and this is a negative, so I have exponential negative N complex conjugate C0Z. That's my Poynting vector, right? So what do you have? Electric field complex conjugate, that's just a magnitude, right? This is a real. Now here I have to be careful, it's a real part only. Imaginary part drops out. And this 2 exponential is n minus n complex conjugate, right? That gives me 2I kappa, right? 2I kappa, oh, I forgot there is another I omega. I omega I should multiply in, so I actually have I omega. I have I omega, right? So n complex conjugate to give me 2I kappa times this another I actually is real. So here n is real. Here is the imaginary part in the exponent. So what I have then is 1/2 E0 square and mu 0 C0 and the real part n and exponential minus 4 pi kappa over lambda. And this lambda is lambda in vacuum. I have used, say, omega C0, right? Omega over C0 equals 2 pi over lambda. So I substitute this in. And that's how the Poynting vector in a homogeneous medium of refractive index n kappa is changing in the z direction. Here is z. It's an exponentially decay function, right? That decaying exponent alpha is 4 pi kappa over lambda. This is the absorption coefficient. Okay, and the inverse of this absorption coefficient sometimes is called the skin depth. So if the inverse, that's a depth, so you can say when z equals that skin depth inverse, right? Delta equals 1 over alpha. That's skin. When delta z equals delta, we have the field decay to exponential minus 1. Okay. So what do we learn here? You can say that when electromagnetic field propagating in a lossy media, kappa is not 0, right? The field decay exponentially, and that's the electromagnetic wave is absorbed by the medium, right? And in fact, this is very important when you make solar cells, right? This determines how deep the photon penetrate into the material. And silicon is an indirect gap semiconductor, so the alpha is small near the band gap, so it's not a good absorber. And because of that, you have to use a pretty thick material to absorb the photons. And so that is a big problem with the photovoltaics, silicon photovoltaic, the material cost. Okay. Any questions? So this is propagated in the same medium. And the exponential law, so sometimes we can write, so this is a Poynting vector, right? And it's the say the power flux, and sometimes we write the intensity. Intensity is the energy per unit solid angle, right? Intensity propagating in medium is exponential alpha times x, or x is the direction of propagation. This is another way to write the same form. And this is also called the Beer's law. It's a consequence of the Maxwell equation, but it's called the Beer's law. Okay, so if you have a light comes in onto a surface, and what we wrote down here is propagating inside the medium. Okay, so we have not talked about how much is reflected. And what we talked is once you know this field in this direction at this point, the flux, and it will decay exponentially inside, right? So a material could be very reflecting, but very absorbing. What does that mean? It's conflicting, right? So what does that mean is the reflectance is very large, right? The reflectance R is very large. A material could be 99% reflecting. But once the electromagnetic wave gets into the material, the penetration depth is very short. It's absorbed. Those that get into the surface is absorbed in very short distance. In fact, all metals behave that way, right? Metal very reflective, but the field, maybe 1 or 5% of this wave gets into the metal, absorbed typically in 10 nanometers, 10, 20 nanometers. Okay, but if you have indirect gap semiconductor like silicon, this penetration depth can be millimeter, right? If you do millimeter, you want to capture that material, so when you make a solar cell, millimeter means a lot more materials, so it's expensive. Okay, so this is what's the inside propagation, and now let's turn our attention to what happens at the interface, right? The R. What's the reflectance? What's the transmittance? Reflection. At one interface. And this is very similar to the scalar wave from the Schrodinger equation we talked the last lecture. And what we need is the field on both sides of the interface and use the continuity relation. If you think about how we did with the material wave, right? The wave function here, you have the wave function on the left equals right at the interface and derivative equal to each other. So that's how we derive the reflectance transmittance for material waves. And we do the same thing for electromagnetic waves. So what I have here is flat interface 1 and 2, right? And let me make my life slightly easier by saying here is N1. Okay, I can write a capital N1. Right? If I just write a small n1, it means low loss. If I write the capital N1, it means it has loss. Okay? And here I can write the N2, and I'll extend to the case when they're lost. I'll discuss it. Right? The mass is identical, but there are some subtle differences. And I have the z direction. This is my z direction wave propagation. And this is my x direction. And I have a wave comes in towards the interface. This is my k direction. That's the incident wave direction, right? And I have the norm of the surface n, right? So ki here is angle of incidence theta I, and ki is the wave propagation of the incident wave. Right? Two vectors, two lines form a plane. Right? So this plane I call is plane of incidence. This is how I define my reference plane. Right? So I have my plane of incidence. And this is formed by n and k I. These are the two vectors for my plane of incidence. Okay. Now I have to say the field is a vector field. It's perpendicular to ki, right? But I have to define which direction, because it could be any of this direction perpendicular to ki. Okay. But any of this vector I can decompose into the sum of two vectors. Right? So I can always define, if one case is if I think this is my electric field, is in the plane. The other case is perpendicular to the plane. Right? And once you know the solution, it's a linear combination of the two. So any other direction, you decompose the in plane and cross plane, perpendicular direction. And so, but then you have the choice of, now depends on, if this is my electric field, my magnetic field, now if you use the right hand rule, what's the direction of magnetic field? Huh? Coming out, right? So E incident, and that's a vector, and the magnetic field is pointing out. Okay. So there are three names for this. Depends on which one you are willing to remember. It turns out for over this many years, I always get confused. Okay. My simplest, I always say, okay, I like to remember this as a TM wave. TM means transverse magnetic. Okay, so this case, what I draw is a TM wave. That's the magnetic field is perpendicular to the plane of incidence. Okay, so three lengths. The other two lengths is relative to the electric field, then is parallel to the plane of incidence. So here is, you either call it the TM wave, or you call it the parallel P wave, or you use a symbol of parallel. So three different notations, right? What I have here is for the electric field, and here is when I say transverse is what's follow, right? Transverse is TM, that means magnetic field is perpendicular. TE means electric field is perpendicular. So what I'm going to derive is the situation where the magnetic field is perpendicular to the plane of incidence. Okay. And now I need to write, when the wave comes in, I could have reflection. I have transmission, right? So here reflection, the wave vector, and transmission, the wave vector. And in each medium, I have a plane wave form. I know the plane wave form. This is my plane wave form. I do not know the amplitude, right? And my wave vector, I need to relate to what direction the wave is going for the reflected and transmitted, right? So here is my theta r. If I use more mundane angle, theta t, to denote it, right? So I can write, because if I want to write this k dot r, right? R is any point in the plane x, y, z. And k, I have to write it now in terms of the rotation I have. This k, I have to say kx, ky, kz. Okay? And I write my k unit vector, not the magnitude, right? This is the total. The total, of course, is related to omega c, but what's the unit vector is related to direction only, right? So the unit vector, I can write it as, this is the vector direction. So what's my, under my, say, z is k times the cosine theta, right? X is sine theta, so I have really my sine theta I, 0 cosine theta I. And this is my incident wave vector. And my unit vector of reflection is here r. So x direction is still sine theta r, 0. But the z direction is negative now. This is my propagation direction, right? My z direction is negative. So negative cosine theta r. And my t direction, this is unit vector, is sine theta t, 0 cosine theta t. And we encourage you to everybody really get comfortable. It took me many, many years to get comfortable. But say at least you should do your exercise. And let's say I'm giving you TM wave. You can go back and do TE wave and go through the derivation of what's the reflectance, what's the transmittance when wave goes through an interface. And I made a comment in the last lecture when people do electrical, say this material wave Maxwell, Schrodinger equation, we did a Lomer incidence, right? And here you can say I'm doing general any angle of incidence. So you should go back and redo that problem. Any angle of incidence, you'll be able to do it. Okay? So now what I do next is to write the component because I need the boundary conditions, right? Recall for the material wave, Schrodinger equation is the wave function is continuous, derivative of wave function is continuous. And what's my corresponding boundary condition for Maxwell equation? And it turns out that any interface, and this is actually very general, how you derive an interface condition. When you do heat transfer, you do the same. You apply, so when you do heat transfer, you apply your boundary condition you apply your equation, energy balance to both sides of interface, right? So if I have, this is let's say many of you are probably more familiar with the heat transfer. So while I try to write down the boundary condition for this, if this is a liquid, this is solid, right? I'll apply the energy conservation. I say on the solid side, the heat conduction coming towards this interface equals the convection going through the other interface. I'm applying the first law. The thickness is 0, right? There is a heat comes in from here, but my limit is thickness 0, so that term drops out. When you apply first law, you have 4 surfaces in my drawing here, right? So I do the same thing when I do Maxwell equation, or you do Schrodinger equation, how you derive. You apply, say, in the case of Schrodinger equation, and you have your material wave that's in the matter must be continuous, right? With that, you can write the equation we gave before. And here, I have to take that control volume, apply all those 4 equations, integrate over that control volume, and take the limit that the thickness approaches 0, right? And with that, you can write down all your boundary conditions. And the boundary condition is the n, the unit vector of the norm, and d2 minus d1 equals rho surface. This is the real charge accumulation on the surface. Okay. If you have a current flowing uniformly through the material, everywhere you have current density, right? In that case, what's your surface charge density? 0. because everywhere is uniform. When you get your thickness go to 0, that's the total number of charge in this wall, infinite small thickness is 0. So normally this is 0. But if you do your, let's say some of you may work with electrochemistry, right? And in this case, you have absorbed the charge on the surface. And in that case, your surface charge is not 0. Okay? So you can say what is the n dot product means is the vertical component, right? The component perpendicular to interface, because this is n direction. This is parallel to n direction. So basically, the displacement field is the difference is the surface charge, because each surface charge add a Coulomb field on top of it. The addition it gives you the difference in the surface in the displacement field. And then you have the tangential is a cross product to the interface. So this is a parallel component is 0. So the electric field that is parallel to the interface is continuous. Okay. And then you do your magnetic. First is the dot product is 0. And the tangential component is the surface charge. Okay, surface current. Again, the surface current is something that you need to be careful. Really depends on, for example, I give you a case. If I have a graphene sheet, I try to make a solar cell, and graphene sheet is my electrode, right? And when I try to apply the boundary condition, I would say that in that case, because the graphene sheet has a much higher current density than the rest of the region, I will take that as my surface current density. But most of the time, if it's this homogeneous material and you take your infinite thickness, this drops out. So what it also means is the magnetic field tangential component is usually continuous. So basically, electric field is continuous because this D has to be epsilon 2 D2 E2 epsilon 1 E1. But tangential component is continuous electric field, and magnetic field the perpendicular component is continuous, and the tangential component is the difference of the electric current, surface current. The other way to think about surface current is you know that when a wire flew through a conductor current, you got the magnetic field surrounding, right? So when I have a surface current flowing here, I have a magnetic field going in the tangential direction. That's why you have those relations. But that's all derived from applying the Maxwell equation to the interface. Okay, so those are the general conditions. Now I'm going to apply those conditions. I need to write down. I need to do a little bit dirtier work. Write down all those components, tangential and perpendicular component, and they apply the boundary condition. You need to write electric field, magnetic field, so but if you need to develop a habit, right? Yeah, it's all plane wave. That's what I wrote down before. And for the TM wave, where the electric field is what I incident, right? So it's incident. I have 3 waves. One is the incident, the other is reflect, the other is transmitted. I have to write down all of them. to count, right? So this is the incident, and it's a vector because it's not parallel to x or say any direction, right? It has an angle. So, and then exponential, I need to carry my phase factor minus I omega t minus, you go to look at what we have here, k dot r, right? K I already pull out, so omega c0 times n. And now I have ki is sine theta I, cosine theta I 0, right? And r is xyz. So the dot product of these two gives me n1 x sine theta I plus n1 z cosine theta I. So this is where you should be careful. And C0, that's the incident. Okay? And it's really tedious, but say once you get used to it, this is just a phase factor, right? And remember, this one actually has a component because the vector EI, right, has a component in x direction and has a component in the z direction. So this is you can say is EX and 0 EZ, the incident. And you can do your vector decomposition to write down this component. Right. So you similarly write what's the reflected and exponent. And very soon, all those exponents are going to drop off. So I just want to write it to show you how we get this, why it drops out. Minus n1, because z cosine theta r over c0. Recall, right, because this is kr, it has a negative, so I have positive becomes a negative, theta I becomes theta r, and the area is still medium 1, and transmitted let me say parallel, and exponential minus I omega t minus n2 x sine theta t plus n2. I can just look at that times z cosine theta t. I'm just changing my symbol and changing median from median 1 to median 2. Right? So it looks very long. It's just the phase factor. I'm writing out the details. And this is the amplitude and vector of the transmitted reflected, which we want to find out. And in fact, we also want to find out what are the directions. See that reflected direction and transmitted direction. We're not assuming anything a priori. Right? So we have the electric field. We also want to write the magnetic field. And if you check your load for any plane wave, if I can write, that's how in the homogeneous media we derived, right? Given electric field, I can derive the magnetic field. You go to the first equation, you write the other magnetic field component. And then you know, in this case, magnetic field is a TM wave, is only in the y direction. Right? So let me give you, right? This is a E, right? And H is in the y direction. Remember, is HY only because that's the part of the mass you substitute in, and also part of the physics we say we're considering TM wave. So this is only y direction, and you can say that in the it's related to electric field after you use the first equation. So N1 mu 0 C 0 and is parallel of the electric field. So it's related to magnitude of the electric field incident. This is the incident magnetic field, right? And backwards reflected is going backward, so there's a negative sign. The other way to think about negative sign is if this is the electric field and this is the same in the same direction, you can say here E cross H, the H must be going into the board. So I have a negative sign. That's a lateral. If you it's when you substitute it into equation, you'll get this. So mu 0 C 0 and exponential t. Let me write this phase factor is the same. Phase factor is the same as reflected, and N2 mu 0 C 0 and parallel. Oh, this is R reflected. This is transmitted. Exponential phase factor of transmitted. So here we're denoting this one is the phi incidence, and this is the phi reflected, and what's inside here is my phi transmitted. Okay, so what really is tedious is carrying out this phase factor, which will drop out very quickly. Right? Now I'm going to apply the continuity. The electric field tangential component, because I don't have any surface charge, tangential component, electric field and magnetic field are all continuous. Okay? And you see you could apply the perpendicular field is continuous, and either way you'll get the same result. Okay. So let me apply this relation. What I have here is the tangential component. So electric field and my electric field is in the tangential component is Ex, continuous in the x direction, right? If you look at it, my electric field in the x direction, for incident, for reflected, I have to project it into all x direction. And that's the field. You need to sum up each side. It's a total field. It's not just one. I didn't say incident or reflected. It's a total field on each side. Right? Same when we do the wave function. It's a total wave function due to incident and reflection. So this field summation is very different than when you do this. Typically, if you take in radiation, it's doing intensity add up. Now I'm doing the field add up. And that equals the other side. So if I do this, what I have here is EIX. So incident x component, and exponential, I need to carry this phase factor. Z is 0. I was clever choosing my coordinate. Z is 0 at the interface. So all Z drop out. Right? And omega t, I omega t, you look at every term has a negative I omega t, that will drop out. Right? So I'm not going to carry minus I omega t. I'm not writing down z equals 0, and I'm only x. So I'm going to write this x component term is I omega n1 x and sine theta I over C0. That's the incident component in the x direction, and the reflected component in the x direction, exponential I omega n1 x sine theta r equals say over C0 equals transmitted in the x direction exponential I omega n2 x sine theta I over C0. So this is the continuity in the electric field in the x direction. I can write the magnetic field similarly, but I want to do one argument so that I can drop out all those exponents. You can look at this. This equation has to be valid for x point, every point x, right, in the plane. Right? For that to happen, your only way is all that exponential equal to each other. Otherwise, you have zero solution. Right? Because I only have one transmitted, one reflected. So x, if for this equation to have a non-trivial solution, all exponential terms equal to each other. And when I have this omega, of course, doesn't change. And so you can say the n1 sine theta I from here equals n1 sine theta r equals n2 sine theta t. If that happens, it gives me all the exponents are equal. So this is what you learn in high school, right? Optics. The incident angle equals reflected angle. Snell law, right? Incident, that this solution is theta I equals theta r, and n1 sine theta I equals n2 sine theta t. That's a refraction law, right? So this gives me theta I equals theta r, and n1 sine theta I equals n2 sine theta t. Okay, so this is a Snell law. And another way to think about this is if you look back into our general solution, this exponent is kx, right? Kx times x. So what I have here is a kx, the times x. So kx is the continuous. So kx must be, say, I incident equals kx reflected equals kx transmitted. And this is often called the lateral momentum conservation, right? The momentum component in the direction parallel to the interface are conserved for incident, reflected, and transmitted. Right? So it turns out depends on who you're talking to. People use a completely different term. Say, of course, for specular smooth surface, here we say very smooth. We don't have any assumption of surface roughness. In this case, I have incident equal reflection and Snell law valid. And then say, I think you heard me talking about the gradients, Bragg reflection, right? If I have periodic structure on the surface, right? And it turns out this momentum conservation, this momentum is sort of like crystal momentum, is not exactly, you have to always obey it. So the structure, when it has a component in the x direction, in this case, if it's a periodic structure in the x direction, it gives you the structure, the geometrical, component of wave vector in this direction. That's the Bragg condition, right? So when you have a light comes in, say periodic structure, you have reflection only in certain spots, right? In this case, is the crystal provide you lateral momentum. So this momentum conservation rule here, lateral momentum conservation, if you have roughness, your light can go many directions, right? So if you completely random, your reflection actually can go, in the case of periodic, it goes certain spots, and if it's rough, it go all directions, right? So it's here is a roughened surface that provides you this geometric momentum needed to obey the momentum conservation rule. So like I said, depends on who you talk to. And then when I deal with electromagnetic wave, people normally say this is a rough surface and diffuse reflection. You talk to electrical engineer, there you check the electrical literature, they don't talk about rough surface. They always say, okay, is the momentum conserved or non-conserved? Right? It's talking about Simpson. Okay? And so now with that, I drop off all the exponent. You can say here, this equals this equals this. So I have written a lot of complex expressions. Now I'm going to simplify this, right? Let me write here. And I'm going to simplify to have EIX plus EIR equals ETX. That's this gives, the Snell law gives me the X component of the electric field is continuous, right? The magnitude now. The phase factor already taken care of by the Snell law, right? And of course, the EIX is the EI cosine theta I, right? And this is a parallel component. This we're talking about the TM wave plus E parallel R reflected cosine theta R equals E transmitted cosine theta T. So this is written in terms of the amplitude of the incident reflected transmitted field. Now, I have my next relation. This is a magnetic field. Is continuous, right? Magnetic field is a y direction, and doesn't have because it's only y direction. You see, this is all y component, right? So on the first media, I have the sum of these two. The phase factor is the same, Snell law, equals the second medium. So what I have here is N1, and in fact, the mu c cancel, right? Mu c is the same. So N1 E parallel I minus here, the reflected is N1 E parallel R equals N2 on the other side, E parallel T. So those are the two equations I went through I'm looking for. I'm looking for how much is reflected versus the incident, how much is transmitted field versus incident. And I have enough equation to do that, right? So now you go to solve for this ratio, and I have my reflection coefficient is E parallel R, E parallel I equals N1 cosine theta T minus N2 cosine theta I, and N1 cosine theta T plus N2 cosine theta I. So this is the reflection coefficient, and transmission coefficient is 2 N1 cosine theta I, and N1 cosine theta I, theta T plus N2 cosine theta I, same denominator. So those are the reflection and transmission coefficient. It's not a reflectance transmittance yet, right? Okay.
In the first term over on the far right, n2 cosine theta I, is that right? So you're
Right. So you cross this.
not n1.
This is n1 cosine theta t, n2 cosine theta I. Okay. This switch.
n2 cosine theta I.
Right. Yeah. It's different expression. If you look at the t, if you look at if it's a TE polarization, you get slight different expression, but it's similar. So I would not remember this every time I have to check. Okay. But what we have now is the magnitude of reflected and transmitted fields. And based on this, I can go further, calculate the Poynting vector. Right? I will calculate my Poynting vector. Because I want to find the energy. So your Poynting vector, and you can say for this case, you have a component in the x direction. You have a component in the z direction. And what you really care when you go through an interface, at least if you look at transport in the interface direction, is what's the component in the z direction, right? That's the energy flux going across the interface, right? So if you check your Poynting vector, and we will define reflectance. R equals parallel in the z direction, reflected, incident in the z direction, and you see it's just a reflection coefficient square. Okay, and that's because if you go to check your load Poynting vector S in the homogeneous media, you will say there is something like a complex refractive index. But because it's in the same media, that cancels. Okay, so that's just a few pages ago we talked about at the beginning, right? And transmittance. In fact, maybe I should have used transmissivity for a flat surface. As I said, if you do rigorous, it's an intrinsic material property, right? But if you have rough, we do reflectance, transmittance. If it's intrinsic, it's reflectivity, transmissivity. And here is the ideal. And so that's if you have ideal surface, you always have this. So transmittance, tau. This is it doesn't matter whether it's a parallel or perpendicular wave. But here, what I have is for transmittance, I have to be careful because the Poynting vector is going from one side to the other. So I have n2 cosine theta t, and real part of n1. So this is when the theta I. This is when both sides have, say, complex refractive index. Okay, that's this here is where it's a little bit more complex. Okay, so here is called the Fresnel coefficient, French. So Fresnel coefficients for reflection transmission at the interface. Here is for parallel polarized. So that's the electric field is in the plane of incidence. And let me put a parallel here. And if it's a electric field in the perpendicular plane of incidence, you go through the same derivation, and there are different set of Fresnel coefficients. And here gives you the reflectance and transmittance based on those coefficients. Okay. So let me make a few more comments. Right here we say this is we discussed the name here. This is a TM. The other name is, so here is TM wave. If the electric field is perpendicular to the plane of incidence, it's called the TE wave. And this is the S and perpendicular sign. So it depends on which book you read, you use its own notation. And in fact, say there is even more confusion if you read a different book. And sometimes people write n equals n minus I kappa. Okay? I wrote n plus I kappa, right? And that depends on whether in this wave factor, plane wave expression, whether you put a negative sign in the front. If you don't use this negative sign, you should have n minus I kappa. So I like to put a negative sign so that this is n plus I kappa. Different book use a different notation, and there's no consistency. I can't solve that problem. Okay, the other is, let's look at those expressions. And in fact, you read the Pendry's paper if you have done, you're doing your homework, right? He used exactly what we have here, Snell law, for a surface wave, for when the epsilon and mu is negative, and sometimes this goes to infinite. This R itself goes to infinite. What does it mean that R goes to infinite? It just means that there's no wave can come in and couple to the surface. So in that case, what it has is a surface wave, and the wave decays exponentially from both sides of the surface. Right? So what it had is a wave that decays exponentially from the surface, both sides. And this is where he was discussing different solutions of the Maxwell equation. So hopefully you'll see that it's not too far from what we discussed. You just need to recognize those. And also, when theta I is 0, that's a normal incident, right? When theta I is 0, cosine theta t, all those are 0. So what I have here is R equals n1 minus n2, n1 plus n2. Right? So if you go to check for the material wave we derived at the last lecture, it's k1 minus k2, k1 plus k2. It's the same expression. And in fact, you can write into k. Pendry used k completely. Pendry's paper. You go to read, he used k, he didn't use n, and so that he can have epsilon. He did not use n, because whether you take a positive root or negative root, that's where the debate there, right? So, but in this case, R is, right, the reflectance R is the R square. So giving you order of magnitude. So you can see it's very similar. The wave expression are very similar. Reflectance, transmittance, right? But let's say glass, right? Glass N is about 1.5. Right? How much reflection each interface of glass has? Air is 1. So 1.5 minus 1.5. Divide by 2.5. That's 1/5. Square, 1/25. 1/25 is what? 4%? Right? So a typical one glass interface gives you 4%, and glass has two interfaces. So that's 0.96 times 0.96. So glass transmittance is about 92-93%. Right? It looks like fine unless you really care about efficiency. At 92%, if you put a silver glass layer there in solar cells, and any gaps, and you'll get say below the 90%, you get lost 10% of your energy. That's a lot, right? Sometimes it looks small. Secondly, if you look at the silicon, right? So it's good to remember those numbers. Silicon N is about 3.5, right? So 3.5 minus 1, so silicon interface, how much reflection is 2.5 divided by 4.5 square, right? 2.5 divided by 4.5, that's about 50%. 50% square, 25%, right? So the glass interface reflection is about 25, 30%. If you heat the silicon, if all the light is absorbed, but of course in between the gap you don't get absorbed, then the emittance of silicon then is about 0.7, because the reflection is 30% and the rest get absorbed. Absorption equals reflection. The absorption equals emission. That's Kirchhoff's law. So this gives you now the value that you are saying and you can appreciate. Okay? We'll continue next lecture.